We thank you today for joining us for this webinar, Choosing the Right Transition Techniques for your IPv6 deployment. As we begin, kindly tap in the chat section if you can hear me and tell us where you are from. Before starting, here are some house rules for the success of this webinar. All the controls are at the bottom of your screen. For any questions related to the webinar, please use the Q&A section. For all other needs, technical problems, slides, sound, use the chat section. At the end of this webinar, we will be sending you a survey. Please fill it so that we can improve ourselves. Our presenter today is Bashir, trainer at Afrinic. He will be assisted by other members of the training team who will be moderating this session, providing technical support and taking your questions from the chat and during the Q&A session. We look forward to a fruitful, enjoyable, and above all, an interactive exchange. Over to you, Bashir.
Thank you, Emma, for that wonderful introduction. And I hope you can hear me, right?
Yes, we can.
Okay, good. So I can see from the chat, we have quite a diverse audience over here. So welcome Diren, welcome Peter, welcome Uluwasun, welcome Guy, welcome Radek. Yeah, thank you very much. So this webinar will be all about IPv6 transition techniques and how you can choose the proper transition technique for your IPv6 deployment. So I know before we even begin, transition techniques might be, can you call it higher up the ladder in terms of IPv6 deployment, but it's always good to have a clear picture, even as you're doing your IPv6 deployment. So even if you haven't started deploying IPv6 or if you're currently working on it, we're always here for you. And I hope these discussions will inspire you to start if you've not started and continue with your IPv6 deployment. So as Emma mentioned, I'm Bashir. I'm a trainer here at Afrinic, mostly involved in crafting courses and also assist in the IPv6 deployment support program, which is headed by Willie, whereby we help operators to deploy IPv6. So our agenda today basically will be, we look at why we need transition techniques, and then we look at what are the available transition techniques that are available or that are there, right? And our scope will focus on DualStack Lite, MapE, MapT, and 464X Lite. Then once we look at the transition techniques, we look at which transition technique is suitable based on the network type. Then as usual, at the end, we'll handle your Q&A, but always feel free to type in the Q&A section if you have any questions. And as I usually encourage, it's usually good to hear from you as operators. What have you been doing? What challenges you've been having? So that we can also learn from each other. So we don't want it to be like one way, right? From our side, we're not like 100%, right? So it's a learning process whereby we share information. We can also get to learn new things from you guys. So let's begin with why we need IPv6 transition techniques. And before we look at that, there was some last month, AWS enabled IPv6 only subnets and EC2 instances. And this was big news because the use case for this, you will have, if you're doing serverless applications or using containers or doing setups which require a lot of IP addresses, so you may need to have IPv6 only subnets and EC2 instances. And then in combination with this, AWS launched NAT64 and DNS64 capabilities to enable communication between V6 and V4 services. So in this webinar, we look at NAT64 and DNS64 towards the end, and we'll also look at why we need IPv6 transition techniques. So if you look at IPv6, it's not new, right? As I usually say. So we had IP 1981 in the early 80s. And then after that, in 1994, we had this RFC 1631. And if you just read, I'm not going to read everything over here, but if I quickly read the first line, the two most compelling problems facing the IP internet are IP address depletion and scaling in routing. So you can imagine this was in 1994. So the notion of us running out of addresses, it was foreseen way back. And then in 1996, to mitigate these problems, we had RFC 1918, whereby we now had the luxury of using private IPv4 addresses and the public IPv4 addresses over the internet, private IPv4 addresses internally, just to conserve these IP addresses. And then in 1998, again, to mitigate this, the long-term problems of depletion, address depletion, IPv6 was initiated. The first draft came out. So between 1998 to 2021, what has happened? We've had some network operators who were early trendsetters deploying V6 in the early days, in the early 2000s. And of course, it was really problematic, right? Because you encounter a lot of issues which people have not yet encountered. So we encounter issues and go back to ITF, draft RFCs, and make improvements to the protocol. But we can say for up to this point, things are looking much better. At least when we look at the deployment of IPv6, it's improving. And since we have operational experience, so not deploying IPv6 should not be an excuse. So why transition techniques? First thing is IPv4 and IPv6 are not compatible. Remember, IPv6 was introduced so that we can have a new protocol which doesn't have address shortages or limitations, right? But when you have the new protocol, we're still going to need IPv4, right? We're not going to have like a flag day whereby we just switch off all IPv4 and we migrate to IPv6. So the second reason why we need transition techniques is both protocols need to coexist, at least in the near future. So IPv4 and also IPv6. And then transition techniques will help us with the gradual transition to IPv6. It's foreseen that once people start deploying IPv6, IPv4 will gradually disappear. Of course, this will take time, right? How long? It's time, only time will tell. So before we begin, I usually like to ask this question every time I run my webinars, just to understand where we are in terms of IPv6 deployment. So I'd like you to head over to menti.com and help me answer this question. What stage are you in with regards to IPv6 deployment? Menti.com, and then use the following code. Let me make it easy for you. So you can scan the QR code on your screen, or you can enter the code 48756887. So what stage are you in with regards to IPv6 deployment? Last time I did this, there was a close tie between no plans. Last time I think I had 10 guys who had no plans and 10 guys who had advertised their IPv6 prefix. So hopefully today I'm going to see a much improved stats. So what stage are you in with regards to your IPv6 deployment? Do you have no plans? Are you still in the planning phase? Have you advertised your prefix? Have you gone ahead and enabled V6 in your core? Do you have V6 on a test VLAN, or do you have customers on V6? Of course, the ideal situation is the last one, right? We have customers on V6. I'll be very happy to see that one winning. But all the same, whatever stage you're in, it's always, you're not alone. Good, so I see 21 guys, and we are 45 of us. So 3 more and we can move on. And then at least today I say no plans, very few people. So it's a good sign, a big improvement from the last time we did this survey. Okay, so let's move on. Thank you so much for your participation. So as mentioned earlier on, this webinar is all about transition techniques. So I'll start with an overview. We look at the overview of transition techniques, which can be in 3 categories. We have dual stack, we have tunneling and translation. So we're going to look at all these 3 individually, and each of them will have, of course, tunneling and translation will have specific transition techniques which implement these mechanisms, tunneling and translation. So we'll start with dual stack and then look at DualStack Lite, lightweight 4/6 and MapE, and then look at MapT and 464 XLAT. So remember, this is just like a 1-hour webinar. So we're not going to cover like each of these transition techniques in depth, right? So my goal here is to just spark enough interest for you to be able to go back and implement these transition techniques. And we also have a course which will share the details later on. We've developed a very extensive course on all these transition techniques, which you can review later. So let's begin with DualStack, right? So DualStack just involves running both IPv4 and IPv6 protocols on all the nodes along the path, right? So with DualStack, DNS is key to the operation of DualStack. So DNS reply determines the protocol stack to be used. And then Happy Eyeballs improves the user experience behind DualStack, whereby if you have a node with IPv4 and IPv6, and there's something wrong with IPv6, right? Remember, usually for most implementations, Windows Server, most operating systems will always prefer IPv6 by default. But what if there's something wrong with IPv6, right? And we're preferring IPv6. It means that there'll be a visible delay once we start switching from IPv6 to IPv4. So Happy Eyeballs helps with this, and we'll see this in a short while. So how DualStack works, right? We said it's pegged on DNS. So DNS is key on the functionality of DualStack. So on my left, I have a host trying to connect to the server example.com. First thing it does is send a query. Remember, the host is DualStack, right? So it's going to send a DNS query for the A and quad A records. Then the server is going to respond with the IPv4 and IPv6 address. And then next, establishing the TCP session, we're going to send the SYN for both protocols, for both IPv4 and IPv6. Then, of course, the server will respond. Over here, we're assuming the server is also DualStack, right? If the server was not DualStack, we'll either get an A record only or just a quad A record. And then the host will determine what to use. So the server is going to respond with both the SYN and SYN-ACK, and then the host is going to acknowledge with the chosen protocol. In my scenario here, I'm just assuming everything in the path with V6 and V4 is okay. So the host is going to use V6 by default. But if there's something wrong with V6, it means that we may not get the SYN-ACK for V6 or something like that, and the host will just fall back to V4. So you can see this reduces the delays, user visible delays. Because imagine if we were sending the SYN first for V6, right? And then the server has an issue on V6, or along the path is an issue with V6. So we'll have to get back maybe retransmissions or issues with the V6 path, and then the host will now initiate the V4 connection again, and there'll be a delay in between. But this time around, we're just sending initiating the connections on both the protocols, IPv4 and IPv6. So of course, doing this DualStack is, and we've seen this whenever you're starting, most people are starting out with IPv6 deployment, they'll start with DualStack, and most networks will be running DualStacks. That is both IPv4 and IPv6. Reason being, it's very easy to roll out. If you have V6 support in your equipment, all you just need to do is enable V6 if it's on your edge routers, configure your IPv6 addresses on the point-to-point interfaces, enable BGP, and continue rolling down your deployment to the core until you get to the customers. And then the other advantage with DualStack, it's easy to discontinue IPv4 when all services are on IPv6. So once IPv6 is running well, you can easily just shut down IPv4 gradually. But it has disadvantages. You still need IPv4 addresses. So every time you're deploying, you also need to cater for IPv4, which also means IPv4 addresses. And then you'll also be having additional monitoring, troubleshooting, security policies. So in short, it's a lot of work. But as I said earlier on, most networks will start with DualStack. At least if you can get to DualStack and then move to the other transition techniques that we'll be talking about in this webinar. So I have an interesting question here. So we've talked of DualStack, right? You have your router, you enable both the IPv4 is running, you enable IPv6 on it. So by you enabling IPv6, does it mean double memory and CPU? So I like to, as usual, head over to menti.com. So the slide should have switched if you're still there. So does enabling DualStack mean double memory and CPU? So I see one yes. So will the yes catch up to the nose? So you have your router, you have your Windows device, your Linux box, and you enable DualStack. Does it mean that this device is going to consume double memory of what you're already consuming in IPv4? So of course, the answer, as what we have with the majority, is no, right? Because remember, if you look at the TCP/IP stack, at layer 2, what determines whether to use IPv4 or IPv6, we have what we call the ether type, right? So by enabling IPv6, it doesn't necessarily mean that you're going to be consuming more CPU. Your device is going to consume double the CPU that is consuming right now and memory, right? Of course, there'll be a slight increase, but it doesn't mean that it will be twice as much. So don't be afraid to enable or to configure DualStack at least. And like we said, DualStack is, when you saw the cons of DualStack, right? It's not a long-term solution. It helps you to start your journey towards IPv6, right? Then once you have, and it's a safer option, right? You have V4 and V6 running. Something happens on V6, V4 is still continues to work, right? So that's why many people will will start with DualStack as an option. So the next transition technique is DualStack Lite. So you started from DualStack, you have IPv4, IPv6 enabled. Then we move to DualStack Lite. So DualStack Lite basically is an improvement from DualStack, whereby your access network is IPv6 only. So this means that you'll be able to have some IPv4 address savings on IPv4 address usage. And basically it has two elements, the basic bridging broadband, the before, and the address family transition router. So like we'll recommend later on, right? Some of the transition techniques, people who started deploying IPv6, let's say in the early 2012s, 2013s, so they've already gone through this transition technique. So, but it's important for you to know what's available out there. So for DualStack Lite, it combines tunneling and NAT. Remember I said that your access network is IPv6 only. So for you to be able to send IPv4 packets across your IPv6 only access network, you're going to do some tunneling, V4 in V6. And then NAT is going to be done on the address family transition router, right? So the B4 device is your CPE, and then the AFTR is your tunnel concentrator, which does NAT. So for DualStack Lite, we also use IPv4 address sharing. So let me show you a diagram which can explain further. So we have the B4, the basic bridging broadband device on the left. And this is the CPE, right? And then on the right, we have the AFTR, which does CGNAT, NAT, and then is also the tunnel concentrator. So IPv4 packets will be sent from the host. So for example, we have an IPv4 only host on the top left corner, right? So the packets will hit the B4 device, the CPE, and then they're going to be encapsulated in IPv6 and sent to the AFTR. And then the AFTR is also going to do NAT on it. And then NAT being done on the AFTR means that you need to have an extended binding table. So what do you mean by the extended binding table? So the extended binding table basically has the mapping of the IPv6 address of the B4 device and the source port, source address, source address, destination address, source port, destination port, and protocol. So remember the 5 tuple, right? So you're going to have the IPv6 address of the B4, and then plus the 5 tuple. So it means that when you look at DualStack Lite, everything happens on, most of the heavy lifting is done on the AFTR. And typically this will be a CGN box, right? So it means that if you look at it from the perspective of logging, because DS Lite does what we call per flow logging. So each V6 address plus, so the V6 address plus the tuple, source IP, destination IP, source port, destination port, all this will be logged for each flow, right? So it means that logging requirements are pretty high when compared to other transition mechanisms, which we'll look at later. So this is DualStack Lite, uses extended binding table. Remember, for any device that has V6, we're not going to do any translation. No, and we're not going to do any encapsulation. V6 packets are just forwarded straight throughout the access network, the V6 internet. What is going to be impacted is packets that are originating from V4 only nodes. So the next, before I look at the next transition technique, so the pros and cons of DualStack Lite. Let me clear my screen, then we move on. Just 1 minute. Let me, before I move on, 1 minute, please. Let me clear my screen. Ola, please help me clear my screen. I can't do it from my side. Don't know why. So as Ola helps me with that, so in terms of the pros and cons of DualStack Lite, so DualStack Lite requires IPv4 utilization compared to DualStack, right? So remember, because we are doing an IPv6 only access network, so it means that the IP utilization is going to be lower than DualStack. So it's a step up compared to DualStack. And then the key disadvantage is it maintains per flow state, right? Like I mentioned. So that's the source IP, destination IP, source port, destination port, and protocol. Plus, in addition to that, it also, with the extended binding table, you also need to know the IPv6 address of the CPE or the before device, right? If you go back to our diagram, since remember, our access network is V6 only. So the interface on the before connecting to the IPv6 provider's network is IPv6 only, right? So the extended binding table will have the V6 address of the CPE. It will also have the source IP, destination IP, source port, destination port, and protocol. So for each and every flow that is happening. So that's why the logging requirements are very high for DualStack Lite. And then the CGN is a bottleneck because we have a lot of tunnels ending at it, right? So it's a tunnel concentrator. So we have a lot of overhead in the CGN. So if you want to mitigate this, again, we know CGN, right? Very expensive. So you need to have multiple CGNs for failover and to ensure that the load is properly distributed. So it ends up having CapEx implications whereby you spend a lot of money in acquiring more CGN. And then there is limited number of ports per subscriber with DualStack Lite. So an improvement to DualStack Lite is lightweight 4/6. And how is it improved? So basically, it's improved by moving the NAT function from the AFTR. Remember the tunnel concentrator? So we move the NAT function from the AFTR to the CPE. So it means that we have less logging, first of all, because remember for DualStack Lite, since the logging is per flow, that's IPv6 address of the CPE, source port, destination port, source IP, destination IP. So you're capturing a lot of info, right? And there's lots of logging. But for lightweight 4/6, logging is reduced. And then similar to DS Lite, lightweight 4/6 has two elements: the lightweight before, the basic bridging broadband, and the lightweight AFTR, the light LW address family transition router. So pretty similar to DS Lite. So similar to DS Lite, we also have a binding table to capture the state. And as we mentioned earlier on, NAT is done on the B4 device, not on the AFTR. And this means that you remove your dependence on CGNAT, first of all, and cost will be reduced. Then the binding table will just have the IPv6 address of the B4 device, and then the shared public IPv4 address. And it will also have the restricted port set. So IPv6 address of the before, the CPE, shared public IPv4 address, and restricted port set. So this is what we call per subscriber logging, right? So we know this subscriber connected to this CPE, you can be able to identify them based on the information we have in the binding table. But if you compare it to DS Lite, right? DS Lite is per flow. So if you have 5 devices connected behind the CPE, each of those flows is going to be captured, right? But for lightweight 4/6, the logging requirements are much better compared to DS Lite. But the functionality is exactly the same. So for V6, if you have a device that's using V6 or DualStack, remember when you talked of DualStack, we said V6 is preferred, right? So encapsulation is not going to happen. And to be more specific, if you have the host or the node is connecting to a server that is V6 capable, right? So DNS will do a DNS query, get back the A and code A records, and then the device will eventually end up using V6, right? But if the server does not support V6 or is connecting via V4 only, so then that's when we do the encapsulation. So from V4, we use V4 from the host, and then we do encapsulation at the CPE, the before, And then at the FTR does decapsulation. When the packets are coming back, from the IPv4 internet, we're going to use the binding table to determine which CPE is going to receive this packet, right? So remember, the binding table has the lightweight before IPv6 address, right? So we're going to know where to forward that packet that IPv6 packet once we've encapsulated it. Then the before will receive the IPv6 encapsulated packet, decapsulate it, and then do NAT, and then send it to the relevant host. So that's how lightweight 4/6 works, similar to DS Lite, but with the NAT function moved to the CPE. And then the key advantage with the lightweight 4/6, the state is reduced from per flow to per subscriber. And then reduced state means reduced logging. Then, as usual with the tunneling, you have a lot of tunnels of the softwares, which means overhead in the lightweight after. Then, since lightweight 4/6 limits the number of ports per subscriber, this can be a problem. And then the key thing with lightweight 4/6 in terms of implementation, lightweight 4/6, you can implement it via, there's an open source solution called Snub. I think also Juniper use them. And some guys, I've seen some deployments that were done on Snub. But since it's a virtual machine, there were concerns about like the throughput, which I saw that they were sorted out. So it's very easy to implement using open source solutions, as compared to with the DS Lite. From what I've seen from my experience, DS Lite is done on CGN devices, and CGN devices are very costly. On the other hand, when it comes to the CPEs, remember you need to have support in the concentrator, channel concentrator. That's the FTR, and also the before, the CPE. So in terms of the CPE, DS Lite has very good CPE support compared to lightweight 4/6 and even some other transition techniques we'll look at. So the next, remember we're still under encapsulation, right? So the next transition technique is MapE. So for MapE stands for mapping of addresses and ports with encapsulation, right? And as usual, I see a raise hand. Just use the chat Q&A section to ask your question, and we'll be able to respond. So MapE maps addresses and ports. So you're going to have an IPv6 address, IPv4 address pool. You have a pool of addresses, right? And you're going to map these addresses to ports. So basically what we're doing is we are extending the 32-bit address to a 48-bit address, right? So each address is going to have 535,000 ports. So that's how we come up with that. So for MapE, it has two elements: the border relay, which is the CPE, which is the channel concentrator, and then we have the customer edge, which is the CPE. So you can see for all these transition techniques, they're pretty similar. You're going to have your CPE, which does some functionalities, and then you're going to have either the channel concentrator or the device that does translation in the provider's network. So for MapE, the tunnels provide the direct connection between the BR and the CE. So the good thing with MapE, you're going to provision what we call map rules. So using DHCP-v6, you're going to have what we call map rules. And then for MapE, the most important rule is the basic map rule, whereby the basic map rule will contain a public IPv4 prefix, a set of ports, even though in some instances, you don't need to explicitly say that this is these are the set of ports that this device should use in DHCP. So you're going to use addressing information, the public IPv4 address and what we call extensible address bits to signal to the host the ports that they're going to use, which is more common. And then the CPE also needs to know the IPv6 address of the border relay, right? So all this information is sent via MAP rules, and you do this via DHCP options. So how does it work? So you have your CE, you have your BR. Remember, the access network is still V6 only, right? And then your CE can have dual stack nodes behind it, can have V4 only nodes behind it. So what happens the first time the CE connects to the network is going to send a DHCP solicit message to a provisioning server in your network. So you should have already pre-configured the DHCP v6 options for that to happen. So the CE is going to send a solicit message with the ORO option request option requesting for the MapE container. So because remember we said for MapE, we need, the CPE needs an IPv6 public IPv4 address. It needs set of ports, and then it needs to know what is my exit point, or what is the border relay, the MapBR. So all this information is sent in a container. So the CE does an option request option, ORO, to the provisioning server. The server responds with the BMR, the basic mapping rules. Then these basic mapping rules are the same in a map domain, right? So the map domain should just be a domain which share the basic mapping rule. That is the same prefix and the same public IPv4 address. And then of course the ports are going to be different based on what we call the sharing ratio that has been configured. So the CPE has gotten the basic mapping rules, right? Which determine or instruct the CPE on how to encapsulate the IPv4 packets in IPv6, right? And all this information is similar. The basic mapping rule configured on the CPE is similar in the same domain, right? So when, as usual, like we mentioned, any V6 packets are not going to be encapsulated or tunneled. They're just going to go straight to the V6 internet, right? And then any device that's V4 only, right? So this is what is going to be tunneled or encapsulated. So packet will be sent from the host to the CE. Of course, we're using private IPv4 addresses internally, right? Because the NAT function is on the CE. So first thing that's going to happen is the CE is going to do translation. It's going to do NAT from private to public. Then after doing NAT, it's going to do the encapsulation of this packet. So remember, when we're sending the map rules, the CE is also going to get or configure a V6 address for the tunnel interface. So this V6 address is going to be the source IPv6 address for the encapsulated packets, right? And then we need to forward this packet to the BR. Remember, when the provisioning server was sending the map rules, right? Inside the map rule was the IPv6 address of the BR. So this is going to be the destination address. The IPv6 address of the BR will be the destination. And then of course we'll have our V4 packet encapsulated in V6. So we'll have V4 source, V4 destination. So up to this point, everything is okay. So the packet is forwarded to the BR. Remember, the BR also has the same map rules, right? So it's going to remove the encapsulation and then forward the packet to the IPv4 internet. When the packet is coming back, when the server responds, the BR is going to use the destination IPv4 address. Remember this, from the IPv4 internet, we're receiving an IPv4 packet, right? So the BR is going to use the destination IPv4 address plus the ports to compute the relevant destination IPv6 address, or to compute the right CE where to send the packets to. And this is the beauty of MapE and also MapT, which we'll look at next, because it's stateless in nature. So first of all, it means that your logging requirements are totally reduced, because all you need to do in case you want to correlate activity from a certain user is just check the DHCP v6 logs. So the BR receives the v4 packet and then uses the v4 information, public v4 address. Remember, this is the public v4 address that was allocated to the CPE through the map rules, right? So the BR knows that. So once it checks, it correlates this information against the map rules and computes the destination v6 address, which is this CE. And then, of course, the source v6 address is going to be the BR. And then encapsulates the IPv4 packet that it has received and forwards the packets to the CE. Once the CE receives the packet, this is a v6 packet, right? So it's going to be v6 in with v4 in it, right? v6 with the source, destination. First thing that's going to happen is we decapsulate, remove the encapsulation. And even before you remove the encapsulation, what's going to happen is, because the CE needs to know that this packet is really coming from the right, should be coming from where it's coming from, right? Which is the BR. Of course, routing should have been pre-configured, etc. So encapsulation is removed, and then we remain with the v4 header or the v4 packet, right? And then we need to confirm, even before we start doing that, whether this v4 address, remember it's still the public address, right? Whether this address is part of our pool that we already assigned to this CPE. So these pre-checks are done. And then once everything is okay, next thing to be done is we're going to translate the v6 address we received from, we're going to translate the decapsulated v4 packet. We start with the v4, the v4 public address. We use the NAT table to translate the source IP, not the source. We use the NAT table to translate the destination IP, because remember the destination is a private address, right? So the source IP remains unchanged. And then what changes is the destination IP. Because currently the destination IP is our public IPv4 address that was assigned to this CPE or the CE, right? So what changes is just the destination v4 address. We're going to translate this to the private IPv4 address and then forward the packet to the host that sent the request earlier on. So this is how MapE works in a nutshell. You need map rules, which are the same in your map domain. And then the BR and the CE should have the same map rules. Then using the map rules, the CE is going to compute a v6 address for the WAN interface, for the tunnel interface. And then it's going to use the map rules to know which public IPv4 address to use when doing NAT, from private to public. And then the map rules are also used when the packet is coming back from the internet at the BR. And like I said, this is the beauty of MapE. MapE is quite complex, but it's really preferred because of its stateless nature. Yeah, so in terms of the pros, it's stateless in nature and there's reduced logging compared to Lightweight 4/6 and DS Lite. Because in Lightweight 4/6, remember the AFTR had the binding table, but for MapE, everything is sent from a central location. That's the DHCP v6 server. But you still need IPv6 addresses for the BR, and also subscribers share addresses. So the more subscribers you have, either they get fewer ports or you have a lot of subscribers sharing one address. Yeah, and the limited number of ports per subscriber. So in the same line, when you talk of MapT, it's pretty similar, right? But instead of doing encapsulation, we do translation. And in this scenario, we do double translation at the CE and also at the BR. So similar to MapE, we have map rules. We have the basic map rule, and we also have the default mapping rule. So basically, when you talk of the basic map rule is the same thing we had in MapE, right? Whereby you have the IPv6 address of the BR, you have the public IPv4 prefix, you have the set of ports, and then the IPv6 address of the BR. But this time round, we have what we call the default mapping rule. Because remember, we're not going to be encapsulating the packets, we're going to be translating them. And when we're translating, you're going to translate the source v4 address to a source v6 address. And then the destination v4 address is also going to be translated to a destination v6 address, right? So this is the key difference with MapT, whereby the default mapping rule contains what we call either the prefix 64, which is usually either a network specific prefix, which you as an operator specify, or it can be a well-known prefix. We'll look at this in a short while. And the well-known prefix will be used to translate the IPv4 destination addresses. And you'll see why this is key in a short while. So similar to what we saw in MapE, so the only difference right now is the translation, right? Instead of using encapsulation or tunneling. So at the CE, as usual, like we said, v6, straight ahead, no translation. v4, so this is what needs to be translated. For this node, we assume that it can do v6, right? So it's a v4 only node. So this is where we do translation. Packet is sent to the CE. And remember, similar to MapE, right? Even before everything starts working, right? Before packets are sent, when the CPE is connected to the network, it's going to contact the provisioning server for the map rules. So it's already pre-configured to do an DHCP solicit for the options or the OROs, option request option. And in this case, it will be the requesting for the MapT container, right? And the MapT container is going to have the map rule. We'll still have a basic mapping rule, and we'll also have a default mapping rule. So the v4 packet hits the CE, right? Then we do NAT. NAT would be done first, as usual. So we translate from private to public. And then after doing NAT, we now do the translation from v4 to v6. So remember, the packet will have a source IPv4 address and a destination IPv4 address, right? So first thing to be translated is the source IPv4 address. And then the destination IPv4 address, remember, it's the public address of a server somewhere on the internet, right? So this is where we're going to use the DMR, the default mapping rule, which just has a prefix that you're going to append. So for example, B2001 DB8 : something /96, right? You're going to append the last 32 bits of your IPv4 address, public IPv4 address that you're communicating to. You append it to the DMR prefix, right? And then once that's done, the packet is encapsulated, we send it over to the BR. The source is going to be remember, like we said earlier on in MapE, once you get the details from the provisioning server, the CE computes a v6 address for the WAN interface. And then this v6 address usually has, inside it, it will have the port information plus the v4 address. And this is going to be used to statelessly translate the packet. So let me clear this. So we are at the point whereby this device is sending. So we've said this destination IPv4 address, IPv6 address is going, the destination IPv4 address is going to be translated to a destination IPv6 address. And this destination IPv6 address, we're going to use the default mapping rule, which is just a common prefix that will be used for translation internally. And then the source IPv6 address is going to be the tunnel interface or the WAN interface configured on the CE. Then the packet is going to be sent to the BR, and then the BR does the decapsulation, not decapsulation, translates from v6 to v4, and then sends the packet to the IPv4 internet. When the packet is coming back, you know the drill, right? Since the BR knows, like, the packet will have a source IPv4 and destination IPv4, right? The destination IPv4 should be the v4 address, public v4 address configured on this CPE or the CE, right? So the BR needs to translate these two addresses to IPv6, right? So to do this, it does it statelessly, right? So for the source, remember, so we said you have source IPv6, IPv4, and the destination IPv4. So remember we had the DMR, right? The default mapping rule, which is just like a common prefix used for translation internally. So the DMR is going to be appended on the source IPv4 address. On the opposite side, when the packet was being moved from the host to the server on the internet, the DMR was used as a destination, right? But this time around, we are doing it on the source where the packet is coming from. So we append this prefix to the IPv4 address. And then the destination IPv4 address, remember we are translating from v4 to v6, right? So source v4, we use DMR plus the v4 address. What about the destination? So the destination, this is where we're going to use our map rules, right? We look at the destination IPv4 address and also the port information. And based on those two types of information, those two pieces of information, we are going to know the exact v6 address of the one one interface where we're going to send this translated packet to. So the packet is translated and then forwarded to the CE. The CE receives the packet, does not remove it translates from v6 to v4, first of all. So first step is to translate. And then after translating, we do NAT. And then after NAT is done, the packet is forwarded to the host at the end. So similar to MapE, but with translation. Instead of encapsulation, we do translation. So when you talk of the pros and cons, I'm not going to spend too much time here. Same as MapT. It's stateless and reduced login and still has the same subscriber sharing addresses limitation that we saw earlier on. So unless there's any question in the chat, let me see. Yeah, no questions so far. Okay, good. So in the same line as translation, right? We have NAT64 and DNS64. Remember earlier on we talked of AWS enabling IPv6 only subnets and instances. And for these IPv6 only subnets to talk to IPv4 only services, we need to have a transition technique. And NAT64 is what they use. NAT64 together with DNS64. So it enables v6 to v4 only communication. And then NAT64 translates headers. So remember, you're translating the IPv4 header to the IPv6 header, and then also translates the addresses. And to translate the addresses, we have two options. You can use the well-known prefix, the /96, or you can use your own prefix. And this is what, remember in MapT, right? So this is the exact address I was talking about. You can either configure a well-known prefix or do a network-specific prefix, a /96. And then from this prefix, we're going to merge it with the IPv4 address, usually in hex, to give you a 128-bit address, which you can use either as a source or destination. Yeah, so that's NAT64. And then it works in conjunction with DNS64. So you can't just have NAT64 working on its own. So you also need DNS64. But we'll look at other scenarios in a short while. So for NAT64, you have the v6 only clients in terms of elements, infrastructural elements. So you have v6 only client talking to a v4 only server. Then you have a NAT64 translator, which translates the headers from v4 to v6 and the addresses from v4 to v6 and vice versa. So let's look at DNS64, right? So we've talked of NAT64. So what if, remember when you talk of the infrastructural elements, so we say the client, the host is v6 only, right? v6 only client communicating to a v4 only server, right? So this server will only have an A record, right? In terms of DNS. So it will have an A record pointing to 192, blah, 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 an IPv4 address, right? So for us to ensure that this v6 only client talks to this v4 only server, we need to sort of like play tricks on it, right? Or fool it by using DNS64. So what DNS64 does is to synthesize a quad A record from an A record, right? So the server, the host, the v6 only host does a query, and then apparently the server is v4 only, right? But since we've enabled DNS64, what's going to happen is it's going to synthesize an IPv6 address based on the code A on the A record, and then return this synthesized code A record to the server, to the host. So let's look at how DNS64 and NAT64 work. So we start from, I'll just be highlighting with my pen so that you can understand, right? So the client sends a query, example.com, to the DNS64, to the DNS server with DNS64 enabled, right? Then the server does another query, what's example.com, gets an A record response only, right? Once it gets an A record response, in the response, it means that the server is v4 only. So the next step is going to do is to synthesize an IPv6 address. And you see in this case, we are using the well-known prefix, but you can always configure a network-specific prefix on the DNS64 server. So the code A is synthesized and sent back to the client. That's step number 4. So the client knows, okay, this server seems to have IPv4, right? IPv6 on it, but it's v4 only. So next step, step number 5. So the client has a destination v6 address, sends the packet to the NAT64 device. So remember, the well-known prefix or the network-specific prefix configured in the DNS64 server should be the same as what is configured on the NAT64 server, right? So NAT64 device receives the packet and then does the translation from V4, from V4 to V6, translates the header from V4 to V6, and then translates the addresses, source address and destination address from V4 to V6. Then once that's done, the NAT64 device is going to forward the packet to the web server. So remember, when it's doing the translation on the NAT64 device, you're going to configure pools of addresses, V4 pools that will be used to translate your source IPv4 address, IPv6 address to an IPv4 address. Remember, the client is V6 only, right? So when you're sending the packet with source V6 and destination V6, right? When it hits the NAT64 device, it's going to translate the headers in the packet and then also the addresses. So the source V6 address is going to be picked from one of the addresses in the pools over here. And then the destination V6 address is going to be translated based on what was synthesized, right? Remember, we synthesized this V4 address, server's V4 address 192.0.2.1 to synthesize in the DNS64, right? So this is going to be the destination when we're translating. And then once the NAT64 rebuilds this packet to IPv4, it's going to send this packet to the server. The server is going to respond, right? That's number 7. Then the NAT64 device is going to do the translation. So since it's stateful, it knows the initial communication that was done, right? So it knows that we need to translate the source IPv4 address, which is coming from the server, to an IPv6 address. And then the destination IPv4 address, which was in the binding table in this NAT64 device. And then use this information to build an IPv6 packet, which is going to be sent to the client. As usual, the source or the destination, right, is going to be the synthesized. The destination is going to be the client's IPv6 address, and then the source is going to be the synthesized IPv6 address. So that's how DNS64 and NAT64 combine to provide translation. And in this case, it's stateful. But remember, for this scenario, on me, can't seem to clear my screen again. So the biggest problem with NAT64 and DNS64, you can't use it alone, at least realistically, right? Reason being, it relies heavily on DNS, right? So if you have applications that use literals, it means that they're not going to work, right? Because the client is V6 only, and then it's trying to connect to the V4 only server. So it sends a DNS query. But if the application does not send a DNS query, it means that this whole procedure is not going to work. And we'll see improvements to what have been done to make this usable. Ola, can you help me clear the screen? I still have the issues. Thank you. So let's look at the pros and cons of NAT64. So the major pro is that it enables V6 only to V4 only communication. If you look at the encapsulation and tunneling, communication can only be done between, it stays between the same protocol. So if you're doing V4, you tunnel over V6, and then the server is V4. But for NAT64, it can enable V6 only to V4 only communication. Then subscribers share many addresses. Remember the pool that you configure on the NAT64 device. So subscribers will be sharing that. Then there's no limit in terms of number of ports. But the biggest disadvantage is it doesn't work with literal addresses, and clients must support IPv6. So in terms of translation, the next transition mechanism is 464 XLAT. And basically for 464 XLAT combines stateful and stateless translation. For stateful, it's exactly the same as what we've discussed with NAT64. It remains the same. But we introduce stateless translation on the customer edge device, or on the CPE, or on the user equipment, right? And then for 464 XLAT, it has minimal resource requirements, and it has two components. The PLAT, which is stateful, the provider-side translator, and then the client-side translator, which is stateless. So let's look at how 464 XLAT works. I'm going to explain this diagram with my blue marker over here. So remember the key thing with taking us back a little bit, right? With the NAT64, we said that you have a v6 only device connecting to a v4 only device, but it doesn't work with literals, right? If you have an app that only supports IPv4 and doesn't do DNS, you are out of luck. So what 464 XLAT does is to introduce a client-side translator, which does stateless translation first. So we're going to translate from v4, it will translate from v4 to v6. Then the packet can traverse through the IPv6 only access. And then when you get to the provider side translator, is going to do the stateful translation from v6 to v4. And this is why probably the term 464 XLAT comes from 46. So you're translating from IPv4 to IPv6 and then to IPv4. So how it works, right? So you have this v4 only host over here, 192.168.1.2. So as usual, even before these devices start communicating, provisioning should have been done beforehand. So by provisioning, we need to have the client-side v6 prefix provisioned on the CPE. And in this case, it's a /96, right? So this prefix is going to be used to translate the source IPv4 address. So this and this. Then we also need another prefix, which is going to be used to translate the destination IPv4 address, right? And this is the prefix that is configured on the PLAT. Okay, so let's do the walkthrough of what happens. So we have our v4 only device over here, then it's communicating to the v4 server over there on the right. So the packet is going to be built. The source is going to be 192.168.1.2. So the packet has not yet gotten to the CPE or the CLAT, right? And the CLAT can be your phone, because Android, Apple, they have the CLAT function in them. So the packet hits the CLAT and translation is done. So we're going to use the source prefix to embed the IPv4 address, source IPv4 address. Usually it's in hex. And then we're going to use the network specific or well-known. In this case, it's network specific, since we assume it's the provider's IPv6 address. And then once that's done, we'll have our destination v6 address. The packet is going to be sent to the PLAT, and then the PLAT is going to do the translation. It's going to remove the v4 address, translate the source v6 address to a source v4 address, and then also translate the destination v6 address to a destination v4 address. And then send the packet to the server. So coming back, when the server is responding, So the PLAT, remember the PLAT is stateful, right? So it's going to have this information in its binding table, or in its NAT table. Since the addresses, we had an IPv4 address NAT pool. So we're going to use, so this time around is going to be the opposite when the packet is coming back, right? So the source address is going to be, we're going to use the well-known or network-specific prefix, and then embed, or the right word is not embedding. We're going to map the source IPv4 address to our well-known or network-specific prefix. This is going to be the source. And then based on the entries in the NAT table, which is going to have the source IPv4 address, we're going to build the source IPv6 address and then forward the packet to the relevant CLAT. And then the CLAT is going to translate from V6 to V4. So with 464 XLAT, any applications that use literals, socket APIs will work with 464 XLAT. With NAT64 only and DNS64, literals don't work. And then another key thing is 464 XLAT is the only solution for cellular networks. There's no other solution that works for cellular networks because, like I mentioned earlier on, you have your mobile phone, Android, iOS, will have the CLAT function built into them, and they can be able to synthesize the relevant IPv4 addresses. And then something else, when you're talking of the user equipment, we usually have the address range used for translation, 192.0.0/29. So this is what is going to be used as a source. Remember, most of the time, we assume maybe the device is V6 only, right? And then you have some applications which are V4 only. So this is the scenario whereby you'll need a V4 address, right? Then this is the pool of addresses reserved for transition techniques. Initially, it was reserved for DS Lite, DS Lite, but now all transition techniques can use this IPv4 pool of addresses for translation or for any transition mechanisms. So in terms of traffic treatment, if you're communicating, if the server is V6 only and the application and host is also V6, then there's no translation, right? Everything is end-to-end V6. If the server is V4 and the application and host is V6 only, then it means we're going to do stateful translation. And we're going to do translation only once at the PLAT. If the server and the application are V4 only, right? V4, then it means we're going to do double translation on the CLAT and also on the PLAT. So this is just how traffic is treated. So in terms of the advantages and disadvantages, so first of all, it resolves the NAT64 issues, which we looked at, and it's the only transition techniques that works in cellular networks, and it works with literal addresses and socket APIs, but you still need more addresses for because remember there's a shared pool, right? But the address requirements will be very minimal compared to the other transition techniques that are available. So as we come to the end, so which transition technique should you use in your deployment? So if you're an enterprise network, most enterprise network DualStack will work, right? Unless you're I know there are some large enterprise networks which may end up using the other transition techniques, 464 XLAT, MapE or MapT. For cellular, there's only one option, which is 464 XLAT. So I think in this, if you're a broadband service provider, ISP, so it really comes down to a design decision, because for MapE, like we saw, and MapT, they're really, first of all, once you get the hang of them and learn how to configure them, the biggest advantage is the stateless nature in them, because the border relay and the CEs do stateless translation, and in terms of logging and information, you only use the DHCP v6 information in the DHCP v6 server. But for cellular, 464 XLAT only. In terms, another consideration which I mentioned earlier on is the CPE, right? Because you have your tunnel concentrator or your NAT64 box, but this is the device in your provider's network, right? But you also need to remember the CPE support. So far, I've seen, if you work with the open source CPEs, OpenWRT, I've done at least not DualStack Lite. DualStack Lite is quite challenging to do, to implement, but I've seen OpenWRT will support DualStack Lite, Lightweight 4/6, MapE, MapT, everything basically. And like I mentioned earlier on, the most of the CPE vendors will have support for DualStack Lite, 6RD. 6RD is another transition technique, which has quite some good support in terms of CPEs. So you need to check if you're implementing one of these transition techniques, 464 XLAT, MapT, MapE. You need to talk with your vendor and see if they support these transition techniques. The other thing is, you'll notice that for DS Lite and Lightweight 4/6, there's nothing there, right? Because I think I've seen providers who've transitioned, who started from DualStack Lite and moved to Lightweight 4/6, and currently people are either doing MapE or MapT. So this and 464 XLAT. So these transition techniques are much better in terms of support and implementation. DualStack Lite, Lightweight 4/6 should be better than DualStack Lite, but the biggest problem with Lightweight 4/6 is the concentrator, the AFTR device. But you can use the open source implementation. We said you can use, it's called Snub. And then for 464 XLAT, for the provider side, we just need, most devices will have NAT64 support. And if you want an open source implementation, we have Joule. There's a platform called, there's a software implementation called Joule, which can do both the CLAT and the PLAT. So, okay, it seems we're at the end of this session. So let me look, think we have some questions, right, Willie?
Yes, the first one is a comment. You can read that one loud.
Okay, yeah, if you have an MPLS core, BGP free core, then 6PE/6VP is a good option. Yeah, 6PE, 6VP is a good option, because with 6PE and 6VP, you don't need to change your IPv4 core. So what happens is you're going to advertise the v6 prefixes via v4, and nothing changes in your core. And then second question is, what are the implications of DNSSEC for DNS64?
Yes, for that one, mostly with DNS64, you can break the DNSSEC, but you also have to be aware that if your DNS64 server is aware of RFC 6147, then you can mitigate those issues regarding DNSSEC. That's the most important to know.
Yeah, and yeah, I see some comments here in the chat section. For lightweight 4/6 and MapE, MapT, the approach of ISPs deploying this technique is to have their own CPE developed, which is not great. Yeah, because the biggest challenge, like I mentioned, is on the CPE, right? Which can be a hindrance in terms of progression. So talk to your vendor and see if they support these transition techniques. At least identify a transition technique that works and then ensure that the support is there for this transition technique. Sky Italia. Okay, so this is just some resources for the participants over here about the deployment on MapT. And that's why I insisted for, when you go back to this table that I had shown, the transition technique that you're most likely to implement right now is either MapT, MapE, or 464 XLAT. If you're going lightweight 4/6, you need to do extensive research, because for lightweight 4/6, like we said, CPE, and then also the AFTR. Junos implemented it on, but they're still relying on SNAB, on VMX. So you need to check on that and do extensive tests. For lightweight 4/6, like I said, SNAB, there were some concerns of throughput since it's a VM, but the developer said they had fixed it. I didn't see, since I don't think there are too many deployments of lightweight 4/6. So I don't know the current status behind that. But MapE, MapT, yeah. Then another comment on MapE and MapT, it leans heavily on Cisco, right? Because Cisco are the ones who introduced this, the drafts back then. So most of the support will be on Cisco devices. I think A10 has support, but you need to check. Juniper, not quite sure. You need to check for support. So unless there's any other question.
No question so far. No more
Yeah.
questions.
So if there are no questions, I think this was it's a 1 hour, 30 minutes. Trying to go through all these transition techniques, like you notice, some of them can be quite complex, in quotes, right? So that's why we have this transition techniques course, whereby we explain all these transition techniques in depth. And the good thing, what I like about, let me not say what I like about them, because I might be biased since I'm the one who created them, right? But what I like about them, what we did is, we're not doing videos, right? So it's not just, you don't have me there talking, rambling. So we try to make the courses interactive, and you can at least do something and follow along. So the course is really extensive. Took us some time to develop it, but yeah, you can take the course and it has more details, and you'll better understand all these transition techniques, how they work. And it's really interactive. So use this link to take the course, and then we expect, once you take the course, of course, we usually like feedback from you guys, since these courses help people in the community, right? So give us feedback, and we'll be able to also update our courses. And yeah, the slides will be shared later on, either today in the evening or tomorrow. And so as we leave, this is going to be our last webinar for the year. And I'm going to have some gifts for you, right? Some small gifts. So anyone who takes the course, think the first 5 people, will make the decision. First 5 people to finish this course will give you a free seat to our IPv6 certification. So that's at 36.io. I'm going to type it in the chat, 36.io. So first 5 people to finish the course, yeah, we'll give you free seats to our certification, our silver certification. Someone was asking, where's the link to the course? Okay, thanks for the course link. Yeah, so ensure you register, and we see you later on. So thank you for joining me today. I'd like to thank my colleagues, Willie, Emma, Ola, and thank you all for joining and taking the time.
Yeah, Bashir, there's a quick question also, sorry.
Okay.
How do I have to sit for the certification?
Yeah, the certification basically we do it via Zoom. It's online, and then we do the invigilation via Zoom. My colleague Emma does that. So first of all, if you want to take the course and then we see how it goes, alternatively, you'll visit the link Willie posted there, 36.io/en. We have two levels. We have the silver and then the gold. So I guess most of us will be in for the silver certification. So once you finish the course, I'll be monitoring from my side since I'm the custodian of you guys today. So I'll just be checking first 5 guys to finish. We'll give you that certification. Finish the course and then we'll monitor how to proceed. So usually the certification we offer it at $100, that for silver, and $150 for gold. But anyone who finishes the course from this webinar, first 5 will give you a free seat, and then the rest will give you some discounts. Our goal is to just ensure we get many people certified. Okay, so I think Ola and Willie, unless I forgot something, we should be good to go, right?
Yes, we're very good to go. Yes, no more questions in the chat section section.
Okay.
Yeah.
Okay, so thank you very much, and see you next year.
Yeah. Bye.
Bye.
Bye.